Methane is a loss of energy. Cattle consume primarily grass, and they lose some of that consumed energy in the form of methane. So if we can conserve more of that energy and thereby reduce methane, maybe we can improve performance and efficiency of that animal.
Methane is a fantastic proximate for energy efficiency. We want to make sure that what we feed an animal supports animal productivity as well as animal health, with methane being an important measure for environmental resiliency into the future, as well as into present-day economic resiliency, because we want to think about maximum efficiency. Feed is a cost input into these systems, so we want to think about maximum efficiency throughout that feeding cycle. Methane becomes a great tool for us to utilize and leverage to think about how do we take these really great ag systems, farms and ranches across Kansas today and bring a new level of improved technologies and efficiencies to allow them to think about what they plant in the ground and how that supports what they do when they feed their animals.
And so about 5-6 years ago, people in the physics department at Kansas State University and in agronomy said, well, we have lasers, and one thing we can do with lasers is detect trace gases like methane. And a trace gas is the atmosphere has nitrogen and oxygen, and there's some very small quantities of gases like methane and carbon dioxide that you can detect. They're not a lot of them, but they're impactful. And so you can use a laser and say, how do you use a laser to detect the gas? Well, what happens is the gas absorbs specific colors of a laser, and we know those colors from doing lab measurements. And so if we send a laser out that actually can get absorbed a little bit by this gas, that tells us the gas is there. If it doesn't get absorbed, then the gas isn't there. And this is called spectroscopy, so we can do high-resolution spectroscopy with lasers. And we can use this to measure methane and carbon dioxide and water vapor associated with any kind of agricultural practice.
We look at wind and then other variables in the atmosphere, and then you can actually, based on a concentration measurement, we backtrack and say, okay, the source strength of the flux should be this. And that's how we estimate fluxes.
We want to be able to look at methane on a farm-to-farm system. The idea of having fiber-based lasers, which are much more robust, they can exist in an outdoor system, and you can weatherize them to be able to send light out from a single point source, send it out from that fiber, hit a reflective surface, a retroreflector, and then have that light return to the same source for it to be analyzed. And in doing so, you have infrared light that crosses an entire path that makes one line, and it becomes a line sensor that's completely continuous, so that you're able to look at all of the methane that kind of passes through that through the absorption of that methane interacting with that light. And in doing that, you can look at your initial spectra when you send the light out versus your return spectra where that light has absorbed some of that methane. And that's nice to be able to do it on that one line, but we were looking at an area because we want to farm, so we would do one line on kind of an incoming path and one line on an outgoing path. And in doing that, we have to take into account our gas dynamics, our wind dynamics, and we really leaned heavily into the agronomy side of micrometrology, of actually looking at patterns of how that gas would move.
And that's what really excites me about this project, is we're trying to figure out what can we do or what do we need to do to get herd level emission estimates, because no producer goes and looks at individual animal records every single day, right? We really do need to move to a larger scale to more aptly understand how our management strategies impact the overall system.
And so that's where this research team that has come alongside with their expertise in animal systems and sustainable animal agriculture, laser physics, as well as micrometeorology, they've come alongside and said, how can we push the boundaries of what we can measure and how we can do that in a repeatable way?
Doing this interdisciplinary type of work, you see how other people work as a team and different ideas and how they have synergy and make a product from that. So I think that's one reason why I like it. The other reason why I like it is because physics should be used for helping people out versus just curiosity.
When we feed animals, it's a whole pen. I want to know not just how a single animal is performing, I want to know how that entire lot is performing when they're under one diet.
So whatever we can do, whether it's grazing management, whether it's supplemental feeds, getting the right nutrition into that animal at the right time to reduce emissions, kind of works in our favor 2 different directions.
I think it's important that this kind of project is not about pointing out who creates a lot of methane and how that's a problem. I think the thing that needs to be pointed out is this is the kind of project that down the line, if this was a product or if this was a collaboration where counties could have somebody who goes out and does this. You could have somebody set up and take a week's worth of data on your pasture or something. This is the kind of project that I think would put more control in those producers' hands.